Welcome to today's paper reading. Today's paper is titled, Internet of Agents, Weaving a Web of Heterogeneous Agents for Collaborative Intelligence. This paper was published on the AR14 preprint by Weize Chen and colleagues from Tsinghua University and Peking University. The rapid advancement of large language models has led to the development of autonomous agents. However, existing multi-agent frameworks face several challenges: integrating diverse third-party agents, simulating distributed environments, and relying on hard-coded communication pipelines. To address these issues, the authors propose the Internet of Agents, IOA, a novel framework designed to be flexible and scalable. IOA introduces an agent integration protocol, an instant messaging-like architecture, and dynamic mechanisms for agent teaming and conversation flow control. Extensive experiments demonstrate that IOA consistently outperforms state-of-the-art baselines in various tasks, highlighting its effectiveness in facilitating collaboration among heterogeneous agents. The framework represents a significant step towards creating an Internet-like environment for agents, where seamless collaboration can enhance overall intelligence and capabilities. The code base for IOA has been made publicly available on GitHub. The Internet has significantly transformed how people collaborate and share knowledge, connecting individuals with diverse skills worldwide. This has led to remarkable projects like Wikipedia and the Linux operating system. The success of the Internet in human collaboration raises the question of whether a similar platform can be created for autonomous agents. With advancements in large language models, LLMs, autonomous agents now perform tasks near human level. These agents can break down complex tasks, use various tools, and learn from feedback. To address the challenge of orchestrating such agents, the Internet of Agents (IOA) framework is proposed. IOA aims to overcome limitations in existing multi-agent frameworks, such as ecosystem isolation, single-device simulation, and rigid communication. The framework introduces an agent integration protocol and an instant messaging app-like structure to facilitate dynamic teaming and flexible communication. The IOA framework is structured with a layered architecture, consisting of both server and client components. The server acts as a central hub, managing agent registration, discovery, and message routing, while the client provides necessary communication functionalities. The architecture includes 3 layers: interaction, data, and foundation. Key mechanisms of IOA include agent registration and discovery, which enable the integration of diverse agents. Autonomous team formation allows for dynamic and flexible combinations of agents based on task requirements. Conversation flow control ensures effective communication through a sequential speaking mechanism and a finite state machine for managing group chat states. Task execution involves representing tasks, allocating them synchronously or asynchronously, and managing their execution and reporting. Figure 1 illustrates the conceptual layered architecture of the Internet of Agents (IOA). This architecture addresses 3 fundamental challenges in multi-agent systems: distributed agent collaboration, dynamic and adaptive communication, and integration of heterogeneous agents. The figure shows how IOA supports agents distributed across multiple devices and locations, implements mechanisms for autonomous team formation and conversation flow control, and provides a flexible protocol for integrating various third-party agents. The layered architecture consists of an interaction layer, a data layer, and a foundation layer, which together facilitate agent collaboration through the network. Figure 2 illustrates an example of the nested team formation process. In this example, the initial group chat G0 spawns 3 subgroup chats G1, G2 and G3 for specific subtasks during the discussion. G1 further creates 2 subgroup chats G21 and G22 for a more specialized subtask. Figure 3 illustrates the state transitions in the conversation flow control mechanism. The states include discussion, SD, synchronous task assignment, SS, asynchronous task assignment, SA, pause and trigger, SP, and conclusion, SC. The transition function delta maps the current state and transition decision to the next state. The decision function FLLM determines the next state and speaker based on the set of messages exchanged and the current state. Figure 4 illustrates the major components of IOA through an example walkthrough involving a complex task, writing a research paper on the Internet of Agents. The process begins with client C1 engaging the team formation block to form a group chat with specialized agents. The autonomous conversation flow control mechanism, implemented as a finite state machine, guides the collaboration through various states such as discussion, task assignment, and conclusion. Nested team formation is demonstrated when a need for specialized expertise arises, prompting the creation of subgroups. The message protocol ensures efficient communication and coordination among agents, facilitating a seamless and efficient collaboration process. Table 1 presents the performance metrics of various models on the validation set of the GIA benchmark. The data reveals that IOA achieves the highest overall performance, significantly outperforming models like GPT-4, GPT-4 Turbo, and AutoGPT-4. Notably, IOA excels in the more challenging Level 2 and Level 3 tasks, which require advanced reasoning and complex collaboration. In comparison to AutoGen, IOA demonstrates superior performance in 2 out of 3 difficulty levels, highlighting its effective communication mechanisms and flexible integration of heterogeneous tools. This table underscores IOA's potential as a powerful orchestrator for diverse agents in solving multi-step, real-world problems. The experiments conducted to evaluate the integration of agents, IOA, framework across various tasks demonstrate its effectiveness and versatility. In the GIA benchmark, IOA was tested on a diverse set of real-world questions with a 3-tiered difficulty structure, achieving superior performance across all levels. The open-ended instruction benchmark, comprising 153 diverse instructions, showed IOA's capability to integrate and orchestrate agents with heterogeneous architectures, resulting in a 76.5% win rate against AutoGPT. For embodied agent tasks, IOA was evaluated using the RocoBench benchmark, where it outperformed the Roco dialogue framework in 4 out of 5 tasks, highlighting its robust communication and collaboration mechanisms. Figure 5 presents a comparison of win rates on the open-ended instruction benchmark among IOA, AutoGPT, and Open Interpreter. IOA demonstrates superior performance with a win rate of 76.5% against AutoGPT and 63.4% against Open Interpreter. This performance is consistent across various task categories including math, coding, life assistance, and search and report. The results highlight IOA's ability to integrate and orchestrate agents with heterogeneous architectures, enhancing collaborative problem-solving capabilities. Table 2 presents the average success rates and steps required for task completion in RocoBench. IOA, despite not being optimized for embodied tasks, outperforms Roco Dialogue in 4 out of 5 tasks in terms of success rate. IOA achieves perfect scores on the cabinet, sandwich, and sort tasks, demonstrating robust communication and collaboration mechanisms. IOA's success rates are superior or comparable to central plan across tasks, although it generally requires slightly more decision steps for task completion. This highlights IOA's versatility and effectiveness in managing agents with heterogeneous observation and action spaces. Table 3 presents the results of the Retrieval Augmented Generation (RAG) task, where IOA, based on GPT 3.5, demonstrates performance on par with or better than GPT-4 across all tasks. The best results, excluding GPT-4, are highlighted in bold, and the second best are underlined. The table differentiates between heterogeneous and homogeneous setups, indicating that agents with different evidence pools, heterogeneous, perform better than those with access to all pools, homogeneous. This highlights IOA's effectiveness in managing knowledge diversity and facilitating information exchange from heterogeneous sources. Additionally, the optimal number of agents varies depending on the task, suggesting a task-dependent configuration for optimal performance. In this analysis, we evaluated the performance of 2 team formation mechanisms, regular and nested. For regular team formation, the mechanism achieved a top at 1 recall of 41.4% and a top at 10 recall of 64.9%, with a mean rank of 27.4 and a mean reciprocal rank of 50.1%. In the nested team formation scenario, the top at 1 recall was 59.7% and the top at 10 recall was 81.8%, with a mean rank of 10.6 and a mean reciprocal rank of 66.5%. These results indicate that the nested mechanism performs well in dynamic settings. Additionally, we conducted a cost analysis, finding that while the IOA introduces a communication cost of 53 cents per task, overall costs can be reduced by addressing suboptimal communication patterns, resulting in a deduplicated cost of 74 cents. Table 4 presents the performance metrics of two team formation mechanisms, regular and nested. In the regular scenario, the mechanism achieves a top at 1 recall of 41.4% and a top at 10 recall of 64.9%, with a mean rank, MR, of 27.4 and a mean reciprocal rank, MRR, of 50.1%. For the nested scenario, the top at 1 recall is 59.7% and the top at 10 recall is 81.8%, with an MR of 10.6 and an MRR of 66.5%. These results highlight the effectiveness of both mechanisms in forming precise teams, especially in dynamic settings where task requirements may evolve. Table 5 provides a detailed cost analysis comparing standalone agents and those integrated into the IOA on the open-ended instruction benchmark. The standalone costs for AutoGPT and Open Interpreter are 39 cents and 16 cents per task, respectively. When integrated into the IOA, these costs decrease to 33 cents and 13 cents, but an additional communication cost of 53 cents per task is introduced, resulting in an overall IOA cost of 99 cents per task. This analysis highlights the economic feasibility and potential for optimization within the IOA framework. Figure 6 illustrates an example of repeated communication among LLMs, a phenomenon observed in multi-agent systems. This repetition leads to inefficiencies and increased costs, as highlighted by a nearly 50% reduction in communication costs when repetitions are manually removed. Despite these challenges, the IOA framework demonstrates significant potential for enabling effective collaboration among heterogeneous agents, suggesting future research directions to optimize communication protocols and reduce costs. In the realm of LLM-based agents, recent advancements have enabled these agents to integrate external tools and knowledge sources, enhancing their capabilities across various domains. These agents can now perform a wide range of tasks autonomously, from operating system interactions to software engineering. For example, OS Copilot facilitates interactions across web browsers and code terminals, while OpenDevin focuses on coding and debugging tasks. Additionally, multi-agent systems have been developed to leverage the strengths of individual agents, with frameworks like Agentverse and AutoGen supporting agent collaboration. These systems have shown promise in automating software development processes, though they face limitations such as the integration of diverse agents and distributed systems. The development of these systems aims to create more flexible and scalable platforms for advanced multi-agent collaboration. In this paper, the authors introduced IOA, a novel framework for LLM-based multi-agent collaboration inspired by the concept of the Internet. IOA addresses the limitations of existing multi-agent frameworks by providing a flexible and scalable platform for integrating diverse third-party agents, enabling distributed multi-agent collaboration, and introducing dynamic mechanisms for agent teaming and conversation flow control. Through extensive experiments on various benchmarks, the authors demonstrated the effectiveness of IOA in facilitating efficient collaboration among heterogeneous agents, consistently outperforming state-of-the-art baselines. As the field of LLM-based agents continues to advance, the authors believe that IOA will serve as a foundation for future research and development in multi-agent collaboration. By enabling the integration of diverse agents with specialized skills and knowledge, the framework opens up new possibilities for leveraging existing agents that were developed independently. The authors hope that their work will inspire further research in this promising direction and contribute to the development of more advanced and impactful multi-agent systems. Thank you for watching.